7,700 years ago, the sky over what is now southern Oregon turned black in the middle of the day. Ash began falling across forests and valleys hundreds of miles away. The air thickened, the ground trembled, and within hours, a mountain that had stood for nearly 500,000 years began collapsing into itself. What remains today looks calm, a lake so blue it almost appears artificial. But Crater Lake is not simply a scenic wonder. It is the flooded scar of one of the most violent volcanic eruptions in North American history. And right now, off that same Oregon coastline, another volcano is rising beneath nearly a mile of Pacific Ocean water. And this time, scientists are watching it in real time. Crater Lake descends nearly 2,000 feet, about 592 meters, making it the deepest lake in the United States. Its clarity is extraordinary because no rivers feed it. It is sustained only by rain and snow. The indigenous Klamath people told stories of a great battle between sky and mountain that ended in destruction. Those oral histories preserved memory through symbolism. But the geological record tells us something just as powerful. A mountain once stood here, and it failed catastrophically. Before Crater Lake existed, there was Mount Mazama. Mount Mazama rose approximately 12,140 feet high, about 3,700 meters, comparable in height to Mount Fuji. It was not a single perfect cone, but a massive stratovolcano built from overlapping lava domes, cinder cones, and eruptive centers over roughly 420,000 years. According to the United States Geological Survey, the earliest eruptions began constructing the complex around 420,000 years ago, first forming Mount Scott, which still stands today as the highest point along the caldera rim. For hundreds of thousands of years, Mazama grew through cycles of eruption and dormancy. Lava hardened along its slopes. Ash layers blanketed surrounding valleys. Magma chambers filled, cooled, and refilled. It was part of the Cascade volcanic arc, created by the subduction of the Juan de Fuca plate beneath the North American plate. That tectonic collision generated magma rich in silica, and over time, Mazama's magma evolved in composition and behavior. And then something shifted. Roughly 30,000 years before its destruction, Mazama's eruptions became more explosive. The magma transitioned toward rhyolite, containing about 70% silica. That chemical change made the magma thicker and more viscous. It trapped gases, pressure accumulated. Imagine forcing water through a pipe compared to forcing honey. Water flows freely. Honey resists. Beneath Mazama, pressure built silently for thousands of years. An enormous reservoir of volatile magma accumulated underground, approximately 12 cubic miles, about 50 cubic kilometers. For perspective, that is roughly 10 times the volume erupted at Mount St. Helens in 1980. The system was storing energy on a continental scale, and for generations, nothing visible at the surface hinted at the instability forming below. Then came the final warnings. Shortly before the collapse, the Cleetwood lava flow erupted along the volcano's northern flank. Geological evidence suggests this lava was erupted so near in time to the caldera forming event that when the summit gave way, portions of the flow were still hot enough to drain back into the collapsing crater. That detail is unsettling. It means the system transitioned from active eruption to catastrophic collapse with remarkable speed. And then the eruption began. Around 7,700 years ago, a violent explosion tore through Mazama's northeast side. A column of pumice and ash shot nearly 31 miles into the sky, about 50 kilometers high, penetrating deep into the stratosphere. Winds carried ash across the Pacific Northwest and into southern Canada. Mazama's ash has been identified in 8 U.S. states, 3 Canadian provinces, and even preserved in Greenland ice cores, where it serves as a timestamp in the planet's climate archive. The eruption blanketed approximately 656,000 square miles, about 1.7 million square kilometers, an area larger than the Brazilian legal Amazon. Imagine daylight fading as ash drifted across distant landscapes. Imagine the horizon dissolving into gray. But the most destructive phase had not yet occurred. As magma drained from beneath the mountain, the structure above could no longer support its own weight. Circular ring fractures opened around the summit. The peak began to collapse inward. Entire sections of the volcano dropped thousands of feet. Pyroclastic flows, superheated avalanches of ash, gas, and fragmented rock traveling at hurricane speeds, raced down every flank, reshaping the landscape in minutes. USGS geologist Charles Bacon estimates the total erupted material reached approximately 42 cubic miles, about 176 cubic kilometers. The summit dropped roughly 5,250 feet, about 1,600 meters. What remained was a massive caldera measuring approximately 5 by 6.2 miles wide, about 8 by 10 kilometers, and nearly 3,940 feet deep, about 1,200 meters. And the eruption's influence extended beyond regional destruction. Aerosols injected into the atmosphere cooled northern hemisphere temperatures by roughly 1.1 to 1.3 degrees Fahrenheit, about 0.6 to 0.7 degrees Celsius, for up to 3 years. Some peer-reviewed studies suggest the climate impact may have rivaled or even exceeded the 1815 eruption of Mount Tambora, the event that caused the year without a summer. This is where the contrast becomes powerful. Over thousands of years, rain and snow gradually filled the caldera basin, creating Crater Lake. Its surface appears tranquil. Visitors look out across calm blue water. But beneath that calm lies the memory of collapse, a reminder that pressure can accumulate invisibly before releasing in catastrophic fashion. Mazama is not extinct, it is dormant. The Cascade Arc remains active. The same subduction processes that fed Mazama continue today as the Juan de Fuca Plate descends beneath North America. The forces that destroyed that mountain are still operating. Now shift west, 298 miles offshore, beneath nearly 4,600 feet, about 1,400 meters of Pacific Ocean water lies Axial Volcano, also called Axial Seamount. It sits on the Juan de Fuca Ridge, where tectonic plates are pulling apart rather than colliding. That tectonic difference fundamentally alters its behavior. Mazama formed above a subduction zone, producing silica-rich, explosive magma. Axial produces basaltic magma, thinner, more fluid, more like ketchup than honey. Its eruptions do not generate towering ash plumes. They create lava flows that spread across the seafloor, forming new ocean crust. But do not confuse quiet with insignificant. Axial possesses its own caldera, measuring approximately 1.9 by 5 miles, about 3 by 8 kilometers, with walls rising nearly 492 feet, about 150 meters high, and it is the most intensively monitored submarine volcano on the planet. According to Oregon State University researcher Bill Chadwick, Axial erupted in 1998, 2011, and 2015. Scientists originally anticipated another eruption around 2025, but during the December 2025 American Geophysical Union meeting, that forecast was revised to mid to late 2026. Right now, the seafloor inside Axial's caldera has risen about 4 inches, roughly 10 centimeters, since the 2015 eruption. Researchers estimate that approximately 8 additional inches, about 20 centimeters of inflation, may be required before the next eruption begins. In August 2025 alone, Axial recorded as many as 2,000 earthquakes in a single day. Scientists suggest sustained seismicity near 500 earthquakes per day, combined with rapid inflation, will signal that the magma chamber is approaching eruption. And here is what changes everything. Even if Axial erupts tomorrow, it poses no danger to coastal communities. Debbie Kelly, director of the Regional Cabled Array at the University of Washington, has confirmed that such an eruption would not generate tsunamis and would not disturb the ocean surface. The lava will quietly reshape the seafloor, hundreds of miles offshore. For the first time in human history, we may witness a submarine volcanic eruption in real time. Scientists have deployed seafloor cables, pressure sensors, hydrophones, and GPS-linked instruments capable of detecting millimeter-scale changes. If the eruption occurs while the system is operational, it may be live-streamed to the world. That is the difference between past and present. 7,700 years ago, a mountain collapsed without warning to the people who lived nearby. Ash darkened skies. Climate shifted. The event could only be remembered through story. Today, beneath the Pacific, another magma system inflates. And we measure every tremor, every centimeter of uplift, every pulse of seismic energy. Oregon holds one of the most extraordinary geological contrasts on Earth. The deepest lake in the United States, born from catastrophic collapse, and the most closely monitored submarine volcano on the planet, steadily building pressure beneath the waves. The Earth has always been dynamic. Plates converge, plates separate, mountains rise, mountains fail. Seafloor spreads, magma moves in cycles measured in millennia. The power has not changed. What has changed is our awareness. We no longer wait for the sky to turn black to know something is coming. We detect pressure before rupture. We measure inflation before eruption. We can observe the planet in motion. 7,000 years ago, a mountain vanished and no one could measure it. In the coming years, a volcano beneath nearly a mile of water may erupt, and we will know it before the first lava reaches the seafloor. The Earth is not still. It never has been. Beneath calm surfaces, forces accumulate. Beneath quiet oceans, magma rises. And the next time you look across the blue waters of Crater Lake or hear about tremors far offshore, remember this. What appears stable is often the result of immense forces operating just out of sight.